Okay, hello everyone. So to end our semester, we have a special guest from India, Chandra Tiwary. He's our Istanbul for short. And I'm going to tell you a little bit about him before he started. So he's currently assistant professor in metallurgical and materials engineering department at Indian Institute of Technology, Kharagpur, is it? In India. So he finished his PhD in 2014 from India Institute of Science in Bangalore, India. And he was research scientist at Rice University, where we met, in Houston, Texas, and he has published already 350 international publications, including several high-impact journals and more than 20 patents. He has more than 10,000 citations, and his H factor is 50, over 50. And he is a recipient of several academy and Indian National Academy of Engineering, National Science Academy, and so on and so on. He got a lot of awards. And what else I can say? So what he works on? So he works on development of two-dimensional materials and composites for energy application, development of porous and ultra-low density materials, structure and properties correlation of nanoparticles and its utilization in optical and energy applications. So he is closely working with Indian and international companies for innovation, materials, and development. So thank you so much to be here, and your time now.
Thank you, Chris. You don't need mic, no? You need?
Just for the
Oh, for the recording. Okay. Good. So thank you, Chris, for hosting me, and thank you to all of you for showing up, in the evening. So it's pleasure to be in Brazil. This is the second time, and I was visiting as a print program in São Paulo. Then we decided to just show up here, and there are several reasons to be here. One was we were working on something very exciting, and I realized that I have to come here to finish the work. So once I'm here, then Chris cannot run away, right? So so quickly, before I start my research, the background about institute. So IIT Kharagpur, in short, we call it Indian Institute of Technology, IIT, and it's a beautiful green campus. You have huge plantation. If you wake up early morning, you will see roads, and there is a proverb they say in our IIT, if you walk on the street, you don't get sun because you have big trees. They're covering all over, fairly green. But we have a big history, and the history of this institute started with freedom of the country. So when India got freedom from British colony in 1947, the institute was founded. Now, when they were looking for where they should start building the first technological Indian institute, right, built by Indians for the development. And the Prime Minister realized that we have to catch up technology if you really want to be leader in future, or we want to be sustainable in the future. So they choose this place. Remember, when British came to India, they came to eastern part of the country. And eastern part of the country, that time they used to call it Calcutta. That's what the capital was. So when the revolution started, Indians started revolting against East India Company and British Empire. The people who were fighting for it, they were put it into a jail. And this was the place, this jail was there. Now it's 100 kilometers away from Calcutta, right? That time it was a big forest out of nowhere, best place for prisoners, right? Now when they converted into IIT, it became a good place to do research because you don't have distraction, right? So either you do research or you do research, right? So beautiful, once they are built, after 15-20 years, we got the new building with new infrastructure and so on. This is the campus, one of the biggest campus in Asia. with 3,000 acre of space. 3,000 acre is almost like a town itself. We have everything in the campus, we live there. Literally, we don't have to do anything other than, you don't have to go out of the campus for anything. So self-sustainable, we have around 45,000 of population living inside the campus, families, and we have everything within campus. We have everything set here. And what we produce is number of students, and again, the students who are coming in undergrad with the toughest exam, and our students, they are doing fairly well all across the world. The current Google CEO is undergrad from our department. So you can think of the importance of the institute and what we produce, right? A guy who did undergrad in metallurgy is heading a computer science company, right? So we are completely open discipline. People are, they're ready to do what they want to do. The mixing of interdisciplinary, the culture is very exciting. And again, we have more than 40 departments, 40 departments. The reason is everything what engineering should do, we have it. For example, agriculture engineering. When India wanted to have a lot of research in agriculture, we have agriculture engineering, naval architecture, we have machine learning department and center. So anything which comes up, we keep on expanding. Total, we have now 40 departments and around 45 centers, right? So that's about institute. Now my group, this is my group at IIT Kharagpur. We call it Nano Engineering Research Group, where we have students from different disciplines. And the reason we want to have this diversity is every discipline or every undergrad or master training, you learn interesting stuff which are completely different. Now when you come to do research, if you bring this flavor of different discipline, you can start being creative, start looking at similar things in a different aspect and start building things, right? And those are going to be interesting because a material, if you are developing, and if it's developed by say biotechnologist, and we'll see what they are doing, is going to be different than a chemist when he's making material, right? Because the approaches are going to be completely different, and we'll see that. So overall, we try to have diversity and in discipline as well as other aspect as well. We are thankful to funding agency. The group is funded by national and international funding agency, companies, academia, and so on. So total we have around 4 or 5 postdocs, 26 PhDs, MTech and BTech. So when we talk about materials, right, and one of the big aspects as a material scientist we look at is length scale. When we say length scale, what it means? This is, if you draw the length scale in the circle, the macro scale or meso scale is fairly easy to engineer. You can weld them, join them, cut them, process them. It's fairly easy because you can really see them. Once you make it micro scale, it becomes little difficult, but yes, you can still modify them by controlling processing condition, by heat treatment, by choosing composition, by processing material at different condition, you can modify this microstructure. But if you go further down and bring it something like atomic scale, it becomes almost very difficult to control them. And the simple reason is you can't really see them by your normal tool what you have, by optical microscope or scanning electron microscope. So you can't see them. Handling them becomes very difficult, right? So now when we talk about engineering them, it becomes even more challenging. And that's what our group we are focusing on. We are trying to modify material, control material at this length scale. So what we do really, but if you do, the interesting aspect here is at this length scale, it's very easy to collaborate, work together with theoreticians, because physics, they started with atom, nucleus, and basic component of materials, and now they are coming up to almost the meso scale, or generally they make it of almost 100 or 10 nanometer size. So if you work in this region, we can easily collaborate with theoretical prediction or theoretical simulation, and we are going to see that in the subsequent slides now. So we started with something, first was graphene, and graphene, when I started working in graphene in 2014-13, it was fairly explored. The different methods of making graphene, the physics of graphene was almost into a stage where people started understanding. But as a material scientist, we wanted to understand graphene as a structural material. So in terms of making graphene, which is atomically thin material, if you want to build a structure out of it, one of the best way to do is interconnect them. Now if you interconnect them, join them, you can make a porous object. What you see here, you see this black object or this particular black object, these are foam. Now the interesting point in this foam, they are around 95% porous and just 5% of mass, and you can build this object. Low density, good. Reasonably good strength, that's nice. But what is new it brings into the structure material field, right? Now if you look at structure materials, we have plastic, metals and ceramic. Now each of them has an advantage and disadvantage, okay. Also one of the important aspect as a structured material is plastic has a different range of working. For example, if you take plastic, heat it to 200 degree or even 150, it becomes softer. Metals up to 1000 degree they are okay, not all, some of the metals. After 1000 they become soft. Ceramic, room temperature, they are brittle, they can break. Above 1000 degree they are stable, right? Now if I want to make this object where it should work from liquid temperature, liquid nitrogen temperature to 1100 degrees centigrade, we have to add all those material, right? Now the question is, that become a big problem in material design or any component design, right? For example, if you are making an aircraft which is going to be at low freezing Canada, it's going to land. At the same time, the same material is going to work at 1100 degree high altitude, it becomes complicated. Now the question is, can graphene replace it? And for that, the first testing was done where we make these foams and cool it to using liquid helium and do a compression. So all the way from liquid helium to 1100 degrees centigrade, these foam were tested. And if you see the stress level or Young's modulus, they are almost constant throughout the temperature range. Now this interconnected covalently structured porous material which is made of graphene will have the same strength all throughout the temperature range. And that becomes very exciting, and we can start utilizing this material for a universal application which is independent of temperature. Also being a 2D material, when I say 2D material, what it means, if this is the graphene oxide, if you just be alone or stand alone, they can wrinkle, they can bend and so on. But if I take another 2D material which is hexagonal boron nitride, we can modify the structure. So what you see here folded and crumbled can be a flat by just putting another 2D material. That's open a lot of opportunity, because what we have in graphene is surface and edge, right? Now if you can start combining with different material and you can modify its basic structure, you can build all sorts of interesting structures. And subsequently we keep on doing it, and that is where Cristiano, we work together, and what we have done in this work is we take this porous structure, put a small amount of polymer, the polymer just comes on the edge and get them connected. If you connect them, a foam which is good in compression, they get good tensile strength as well. And that's what we observe in experiment, that you can have a good tensile strength in foam as well by just putting a small amount of polymer which will get connected on the edge. Also you get a lot of advantage in processing material. Now graphene is, when people say discovery of new material, is basically engineering of new material. Graphene, which we are making from graphite, it has been utilized for almost more than 100 years, right? Graphite is there in several industry, all the way from pencil to steel industry. What they do with graphite? Graphite rods, for example, if you buy a high temperature furnace, you use graphite rods. Now the problem is, most of these graphite rod, they are brittle. When I say brittle means, if you drop it, it's going to break. Also, if you want to make this graphite, which is from the powder graphite, you have to compact it to 2000 degrees centigrade to get it solid object. Otherwise, it's going to be in powder form. Now 2000 degrees centigrade is a huge energy. Plus, engineering them become difficult because you don't have really objects, or you don't have source to heat it to 2000 degrees centigrade. So if I want to make a shape of graphite which is complicated, it becomes almost next to impossible. Now what we have done is, we take graphite, convert it into graphene and functionalize them. When we say functionalization, we do a chemical functionalization. If you do right chemistry, you functionalize them, put them together and compress it. at temperature like room temperature or around 200 degrees centigrade, you can weld them, make a porous structure with good rigidity, good mechanical strength and good conductivity. Now graphite, if you are using for any heating source, conductivity is a big problem. If you want to have highly aligned graphite, it means you'll have good electrical conductivity. The cost increases because processing condition, you have to annihilate for very long time. There are several processing challenges comes in. But if you do this graphene route, we can make them nice room temperature or 1100 degrees centigrade. Not just that, what you have is, if you look at foam, they are porous, right? As a result, they are bad electrical conductor. Any foam material, because they have a lot of porosity, they are generally bad conductor of electricity. If you look at foam, they are low density, reasonable strength. But if you look at their conductivity, they are very poor. Now graphene, they are as interconnected, they are fairly strong, the mechanical properties lies better than most of the foam. Electrical conductivity is as same as metal. What it means, the electrical contact which you are making out of tin, copper and so on, you can make them light. So your phone can be much lighter, right? Not just that, they will have good strength as well. And it will be stable from liquid helium to 1100 degrees centigrade. It doesn't mean you are going to put your phone at that temperature, but the graphene if you make, you can do that, right? Having said that, graphene can be utilized to interconnect material as well. So you have two different objects, and this is an example where we take silica, almost like sand, right? If you try to hold sand, they can't hold them together because in most of the oxide, the surface oxide, they don't like to stay together. So if you remember, if you go to seashore, try to hold a sand, they slide. And the simple reason is, if you bring two oxide together, the oxygen on the surface doesn't allow them to come closer and they can slide. What we do here is take a small amount of graphene, put it in the silicon oxide. And what essentially you do here is, think of one atomic layer coming in between this oxide, the two oxide get in or start interacting with the carbon and that acts as an interconnect. Now if you have seen most of the tiles, when they make it, they have to heat it to temperature like 800, 900, but all these you can do at room temperature. And they have good strength comparable to the structural ceramic. Also, you can use this graphene as a coating material. During COVID, this work we started where we wanted to have a coating on top of transparent object. It can be your mobile screen or the shield or glasses, right? Now, the moment you start coating with any object, an antimicrobial or antiviral coating, you start losing the transparency, right? Well, first thing. Second, if you coat with something, if you wash it, it's gone again. So you have to go for coating again because the adherent is crucial as well. Now, graphene being a 2D material and they are ultra thin, if you coat on all these objects, first, they are going to stick there. Second, the transparency is not compromised, still is the same. Now we utilize that graphene and decorate with, and what you see here is, this is the graphene sheet and you see the small copper oxide particles, which are antiviral or that is good for killing virus if they come and stick it. So we started decorating it and start coating on top of it, and it can be easily scaled up. You can coat on any object and get this functionality. So as a whole, we can utilize graphene as a template to decorate other material as well. We also use composite, try to reinforce them with different composite. But the question comes in, after a research of say 20 years in graphene, still it's expensive, right? And there are several companies, several spin-off all around the world. They say that, oh, we are making new graphene and so on. But the question is, can we make graphene in a sustainable way, right? Without putting too much of impact on the environment. Rather, can we use graphene to solve some problems in our society? So we started working with one of the bigger challenge in India or any agriculture country, even Brazil. After growing the crop, what you end up is this kind of waste. You take out the grain, rice, wheat, and rest what you have is the waste material. It's always problem to what to do with it. People end up dumping it, filling it and so on. In India, it's bigger problem because we don't have too much of land to dump things. So what they end up doing is, you have a farm piece of land where you grow a crop. After it's done, you just burn them so that you can grow the next one. Now the moment you burn it, you create this kind of smoke and into analog of graphene, right? And so we build this setup where we treat the agriculture waste, put them under a simple chemical treatment and thermal treatment, and what you see here is making nice layered carbon. It's a mixture of amorphous crystalline carbon with a small amount of silicon. Now if you have that, you can use this nice green graphene, we call it. We can coat on different substrate. We have a company Zelens which is making a gram per batch at around 150 kilo per day. Now where we use this green graphene, in India the biggest problem is, or any country which has a seashore, corrosion is a big problem. Your metal object and mostly steel objects, they are going to corrode. Your window, your structural material, mostly they undergo corrosion. What we do here is, we take those green graphene. It has several advantages. I'm not going to go all of detail. We can control size, we can control charge, and if you make a coating, you can see it is scratch resistance, it has hydrophobicity, and it can make epoxy, which is utilized for most of the anti-corrosive paint. It can improve its corrosion. Here what you see, this is metal epoxy, reduces corrosion resistance, but if you add just 0.1 gram of green graphene, you get multifold enhancement, almost 3 order of difference improvement in corrosion resistance. When we look back, what is the reason? I'm not going to go full detail of it, just quickly for you to understand. These are scanning electron microscope. Epoxy, whenever you use, wherever you are coating, it is going to have this kind of sub-micron pores. For you, you can't see them, right? So you don't care about it. But when you have a salt water will have salt ions, right? Those ions are very small. These small holes or pores are good enough for salt ions to transmit through, right? So after a certain time, they are going to go through here and corrode your object. Now green graphene first reduces these holes. Second, they disperse well, and then if any salt ion even enter, they cannot really pass through the whole structure, right? There are several other aspects. It also improves the surface roughness and so on. I'm not going to discuss that. Improves the surface hydrophobicity, improves scratch resistance. All these things they can do by just taking a waste into a carbon. So currently we have built a bigger setup where we can make 150 kilogram per day, and we have several of technology transfer in paint industry, in spun pipe, we have done that. And this is a book which summarizes different methods of making graphene using waste. We just came last month. Now we can also make graphene from other waste source. For example, e-waste. We can take e-waste, take out the plastic, crush them by cryo milling, take the powder, do laser treatment, and convert them into carbon. Now this carbon we can make ink, make electrical contacts, and so on. Also we can take petroleum waste like petroleum coke. You can take them, do a treatment using solution, and make them nice conducting ink as well. Moving ahead with these 2D materials, the next generation which came in 2011 was transition metal dichalcogenide. What it means? You have a metal which is transition metal moly and a family member sulfur from dichalcogenide. MOS2, WS2 become very popular. Compared to graphene, one of the interesting aspects in this TMDCs were they have two elements, right? So it's not just carbon alone, you have moly and sulfur. Apart from that, another interesting aspect was, if you look at phase diagram where you have a temperature and composition, MOS2, they exist in this phase range. What it means, like a line compound, gallium arsenide, indium arsenide, or all of these line compound, they have a single point of composition, 50-50. If it's off from the composition, it's going to have completely different property. MOS2 has a big solubility range. It means if it's off composition, still it's the same crystal structure. that opens up a lot of possibility. First was you can change moly concentration or sulfur concentration, still it's MOS2, and you can get different size, different morphology, different defect concentration. So if you remember silicon, right, what you do? You do doping, phosphorus, boron and so on, right? Why you do that? To tune the band gap, right? Now the doping has to be very, very small, because if it crosses a certain range, it's going to be different structure altogether. MOS2, you can have 5 atom% variation. What it means? 5 atom is huge, right? In every 10 atom or every 100 atom, you can be 5 plus or 5 minus, still is the same, right? You don't have to worry about precise composition, right? So we started playing around with dope, changing concentration, started making alloys heterostructure. So what you see here is tin dope, moly, tungsten, 2D material alloy. We started having phase transformation. So MOSE2, which is 2H, we can dope with rhenium and have a different crystal structure in atomic. This region is 2H, here is 1T prime. Remember, the one is metallic, another is semiconductor. So you can make this in-plane heterostructure of metal semiconductor at atomic scale. So what you see here, these atoms, you can see this these atoms are atomically sharp interface we can make out of 2 different phases. And all these can be done by changing concentration, changing precursor. What you do is change the precursor concentration and you can have different phase transformation. I get a single band gap. Once I start mixing 2, for example, if you have MOSE2, I start putting tungsten in it. So what will happen? It's going to follow the line here, this line linearly, generally, theoretically. So it's going to have a much bigger band gap. If I keep on doing it, if I can mix 4 different elements, moly, tungsten, sulfur, selenium, we can have the same 2D material. By changing initial precursor, we can tune the band gap from 1.6 to 2, right? Now the question is it possible? And with the help of CVD, optimization of precursor, we can make this 2D material, which is, you can see these atoms. If you can, with a high resolution head of image, we can probe them and you can see all different elements. We can nicely put them in 2-dimensional. Changing precursor concentration, you can tune the band gap of this material, right? So you can play around with this lot of mixing of different materials and make them at atomic thin scale. But the question was, all these 2D material people were talking about so far was van der Waals solid. What is van der Waals solid? Those of you who are aware, most of these are layered material, right? For example, graphite, it has van der Waals interaction among these 2 layers. So this is one layer, this is the second layer. In between layer, they have van der Waals interaction. If you remember your basic chemistry, van der Waals forces are weak, right? And that's the reason you can exfoliate graphite, you can exfoliate MOS2, right? All these can be done. But how many layered materials are there? Among the whole material family, there are a couple of them who fall into layer category. The rest all materials are non-layered. What is non-layered? The layers, individual layer, they have, or 2 separate layers, A or B, they will have a chemical interaction. It can be metallic bond, it can be oxide based, ionic bond and so on. So all these non-layered materials are the bigger family in material group. Now the question is, can we exfoliate them? If you can, then you can make almost any material can be converted into a 2-dimensional material. So the question came and then Cristiano was there. This is molybdenum disulfide in nature. If you go and get this material, this is from Norway, MOS2, this is how they look like, right? You can see they are layered, right? Each individual layer. In Brazil, they call it iron rose. What you find is hematite. Now hematite is an interesting oxide. This is the first material which is found in earth crust. A major portion of your earth crust is made of hematite, which you utilize for steel, iron, right? Now in nature, this is how they are formed. Brazil is one of the big iron ore source and they call it iron rose. If you look at that, they look like layered, right? Now what really happens here? Iron oxide, which is rhombohedral, not a layered material, nature generally deposed by layer by layer. It doesn't grow like a crystal. It grows one layer, then you have some time, second layer, and so on. After a certain time, they have fairly large lateral dimension and anisotropy in another direction because of the crystal structure. Now, if you take this hematite and put them in solution, you can exfoliate them and you can make them into 2D material. Now, this is flexible and it's oxide. It has interesting magnetic property which has been utilized for last 4 or 5 years for almost every application. Sensing, coating, and so on. People started exploring it for all sorts of application. But the question is, if this idea is right, then we can exfoliate several other minerals as well. Country like India or even Brazil, mining is a big business, right? Mining is a big component of our economy. What really we do in mining? We open up, keep on digging, and we take these big blocks. These are the one which is send it for extraction of metals and so on, and you dump this powder, right? Now on top of this heavy metal or mostly metals, this top layer is mostly made of silicates. What is silicate? In the earth crust you have silicon and oxygen, which is major portion of it. At different layer you get different sort of silicon oxygen bonded structure. If you go back to your basic chemistry, these are different form of silicon oxide. In general, the pure silicon oxide, they form into this structure, silicate structure, which is 3-dimensional. Now silicon, the moment you try to grow them, they tend to form this 3D chain and form the structure what you see around. But in nature, the silicate what you saw is different. What they have here, this particular layer is silicon oxide, another silicon oxide. In between, nature dope these 2 layers with all these elements. It will have sodium, potassium, calcium, magnesium, iron, and so on, right? So it's not pure silicon oxide, but because of this doping, you see different color structure, different color in the silicates. Also, you'll have anisotropy. What it means, if I take this piece of structure, think of pulling them. What's going to happen? It can break from any direction. Yes, right? But if I take this structure and try to pull it, what will happen? Here, it's stronger. But this particular direction, it's going to be weaker, right? Let's look at experiment. So what we did, we went back and saw biotite, which is one of the major common silicate, and this is how they look like. You can see they have a layered structure, very similar to what you saw in hematite. And if you keep on peeling off, you can make them transparent, thinner, and so on. So we took several of these silicate, and if you look at in SEM, yes, they are layered. And if you exfoliate them, you can make them transparent, thinner, and thinner possible. And if you do a liquid sonication, you can make 1 nanometer thin, 5 micron lateral dimension 2D materials. Now silicon oxide in 2-dimensional, decorated with several other elements, is exciting for sensing, catalysis, and so on. Any application you are looking at, and on top of that, this is abundantly material, which is available all over, right? Which is really plenty on our earth crust. We don't have to worry about its engineering. It's stable. So far, all the TMDCs or all the material you talk about, the moment you say 2D materials, nanomaterial, the first question comes, is it stable? Right? Because it's going to be reactive. Or the second question you say, is it available? I want in large quantity. If it's not there, you can't use them. Third is it environmental friendly? When I say environmental friendly, it means I keep it in my room, it should not react to human, right? Now silicates are all 3, they qualify for it, right? So we started using them, this flexible material. We had diopside, tourmaline, several of these silicate. We can exfoliate in 2D form. If you can exfoliate, you can coat on any object, you can mix with object, and you can start making 3D structure either coated with biotite or this material, or you can reinforce. Now, what in our group we started looking at energy harvesting by this material. Now, when we talk about energy harvesting, the first thing we look at solar, wind, right? These are big ones. Then you have thermoelectric materials. Now, all these are the last one is piezoelectric material, right? Now, for example, windmill, right? You need to have certain threshold to get a windmill start working and giving you energy, right? Same happens with pyroelectric material or thermoelectric material. But human in our society, we waste a lot of small heats. What is small heat? It can be a vent around you, the AC vent, exhaust, right? Or you're walking on the floor, right? Or your walls where you have a lot of air flowing through. So small amount of heat energy, we generally waste it. And the simple reason we can't utilize those energy is we don't have material which are sensitive to those small forces. Now this 2D material and especially oxides are very sensitive to a very small amount of force. And what happens if you give a small amount of strain, stress or any surface, any force, it's going to start having a change in charge distribution, which can be utilized to get potential, and that's what we do. A small amount of tapping or a small magnetic vibration or even a heat can be utilized to produce voltage. This can be utilized for energy harvesting or for sensing as well, especially for health monitoring or any health related sensing can be done with this. Now with the 2D material, we can mix with cellulose for fabric and we can 3D print them, or we can even coat them and we can add this functionality to your fabric, right? And you can really make patch for sensors, or you can make several other things related to that. We can extend the whole idea and start exploring other 2D materials and look at some interesting properties. Galena, which is lead sulfide, we can exfoliate them in 2D and we can start having non-contact energy harvesting. So what it does, for radio frequency, these 2D materials are sensitive. And the radio frequency, you are talking about what you see in your walkie-talkie. You can set up the frequency in the range. You have this material which is making the contact here with antenna, and you can see it start giving voltage. The LED is growing because of the voltage generation. We can create a volt up to 2 to 3 volt by setting up frequency. Now these kind of ideas are interesting because think of, you have a phone, right? All of us got smartphone with huge RAM, lot of functionalities, right? But one thing you'll see, everyone is carrying charger, battery pack, so on, right? Now you have to go put the charging and so on, right? It become a big mess. If you're driving electric car, you want to charge your car, right? You have to find charging and so on. Aircraft also the same situation. Now, if you want to really charge them without contact, right? What to do? If you want to really have non-contact charging, one of the method is high frequency or high energy based charging methods. Again, you don't want to be in a room where you have a frequency roaming around with high energy, which is going to interfere with your body, right? At the same time, most of the electronics has a frequency, right? Which is okay with our body. Now, normal material which are used for non-contact charging are intense. What we are doing is, we are making sensitive material, much more sensitive than our body, so that they can sense this kind of frequency. And that's what we are working in this called RF frequency harvesting, where we are trying to make these kind of objects or devices which can be kept in your room. You put your phone and automatically it charges. There are several applications we are looking at it. Can we have non-contact remote charging? For example, if a tsunami comes in, right? I think in 2019 in Caribbean they have a big problem. The Katrina was there. It devastated the whole electricity there. Now there was no method to charge there, right? Only method was take battery pack and charge them, right? Now this kind of method you don't need to worry about. You just set up the frequency, they can start charging it up. Again, it's going to be useful for several other things. We started looking at building material which are sensitive to such kind of application. All around us, we use different optical material, and pearl is a jewelry, right? Ornament you use frequently. The question is, if you take pearl and start making them 2D, is it going to be the same color, same optical properties? And answer is no. If you take pearl, make 2D, the optical properties are very different than bulk pearl, right? So we start looking at optical material, try to make them 2D and look at their application for laser and all sorts of optical sensing as well. Now these are all natural materials. Now the question is, can we make artificial material or synthesized material in 2D form where we can control the composition and we can produce large scale. So what we started working on new tellurides which are more stable than sulfide and selenide and has lot of surface charge and surface functionalities. We started working with cobalt telluride which is magnetic, has lot of other aspect, lot of other electronic properties as well. So we make cobalt telluride with 3 different concentration, COT, COT2 and CO2T3. Precisely we can choose the composition, melt the alloy, make a big crystal and then we exfoliate them in 2D form. Same thing we can do with gallium telluride, gadolinium telluride and all sorts of telluride. We can start making them large scale. We utilize them for energy harvesting and recently we started looking at gadolinium telluride for rainwater harvesting. So what happens when it rainfall, right? They are going to hit the floor or earth crust. Now remember they are free energy, but the problem is the drop of water is really light. Piezoelectric material you can't use them because they are not sensitive to small force. What you do here is we make this 2D object which is sensitive to raindrop. Now if you want to harvest energy, remember this water is not neutral, they have a charge as well. Now if you have a 2D material like gadolinium telluride with a huge surface charge, the force, droplet force as well as the charge of the droplet helps you to give energy. Now if you can do that, print on a complex object, put on your roof during rainy season, if think of your solar panel is coated with this 2D material. What will happen? The solar panel doesn't work during rainy season, but because of rain you can still get the power, right? So again we are looking at several of the sustainable energy harvesting. We look at pyroelectricity with a new material like silicon telluride. We look at magnetic behavior of manganese telluride, how thickness dependent magnetic to non-magnetic switching can be done so that we can develop smart and flexible devices. And from 2D we start looking at multi-component alloys where we are making several different elements, put them together in a single crystalline phase where you have all 5 functionality of the element. For example, gold is good for certain reactions, silver is good for another, platinum, palladium, copper. Individually they can do reactions. Now if I put them together in a single phase or single material, single object, what you can do? You can have one material doing all 5 reactions, right? And this is what end up, we start looking at catalysis of this high entropy alloy where you have one nanoparticle. What you see is this 100 nanometer particle which is shown here. If you do a composition mapping, you can see it consists all 5. At atomic scale, this is atom probe, atom probe image analysis where you individually map atoms, APT, where you can see this is a 50 nanometer tip, all 5 elements are uniformly distributed. The head of image also shows a uniform composition. So you have a nanoparticle with 5 elements into it with a uniform composition which utilize for catalytic reaction, sensing and so on. Now if you can make this multi-component alloy or metals, the question comes, we had oxide, telluride, silicates, all these we can make 2D. But can we make metal into 2D form? Now the problem with metal, which it's difficult to make in 2D form, is the crystal structure. So most of the metal, they fall into category of BCC, FCC or HCP. When I say metal means structure metals, right? They are either these 3 structures. Now if you try to pull the structure, the force in all 3 directions are similar. So unlike hematite or silicate what we saw or even tellurides, they don't have anisotropy or high anisotropy so that you can break them. So you don't find metal in 2D form, that limits its application. Now metal, if it's 2D, it's going to be a lot of exciting because metal has much more sensitivity to environment, right? But we can't make them 2D by conventional method. That is where we came here when Cristiano was there at RISE. In metal system, there is a concept called Quasi Crystal, which got Nobel Prize. Dan Sheckman got a Nobel Prize in, if I remember correctly, I think 12 or 13, he got Nobel Prize for this discovery of this new form of crystal. What it is, I'm not going to go detail of it. With the quasi-crystal form, you don't allow to follow the conventional crystalline rule. By normal crystalline rule, it says the 5-fold symmetry and 10-fold symmetry is not possible in crystalline form, and that is the reason these are called as quasi-crystal, right? It's not amorphous, it's not crystalline, it's in between. You can make metals into quasi-crystal form, right? Now if you look at quasi-crystal, you have 10-fold symmetry here, 2-fold symmetry in this direction. Let's make one. So we made quasi-crystal, which is decagonal, consisting of aluminum, cobalt, nickel, and this is the structure looks like. If you try to put a force here, the force along this plane versus pyramidal plane is different. So what will happen if you put in energy? They are going to break in these two directions. If you do that, you can make metal into 2D form. That opens a hell lot of possibility, because quasi-crystal was known for last 30-35 years, and there are several metals which can be converted into quasi-crystal form. We started looking at this direction, and Cristiano, this figure is done by Cristiano if he remembers, and then we did a lot of work in this quasi-crystal, and today we are able to make multi-component quasi-crystal, which we have been utilizing for hydrogen production, oxygen production or oxygen reduction and so on. From water also we can use for sensing or plasmonic application. Any question? How much time I have? 10 minutes?
Yes.
Okay. So, so all this material we talk about, right? There are two things which we put a lot of resources, energy, right, and environment, right? Now the question is, can we make material by a greener method where we don't destroy our environment, right? And can it bring some advantage, right? So if you make a CVD 2D material or any 2D material, you will have this kind of size distribution. It means you'll have a small, big and so on, right? But if you look at in nature, they make things very periodic, systematic and same structure without any external energy, right? Now we take the inspiration and started making materials. I just try to put all the different aspects, but what we do here is we take a Pseudomonas microbe which is extracted from soil, put them in solution and put your precursor. The precursor we have added here is moly salt or cadmium salt, right? And what you do, just drop it and leave. Go on vacation, enjoy your life, come back after a week. If you come back, what you see is the color of the solution has changed. If you do a centrifuge and collect the powder and do analysis, what we can see, we are able to produce moly sulfide or cadmium sulfide quantum dots, right? I'm not going to go detail of it, but just quickly what we want to highlight here is these are microbes, right? And if you look at in transmission electron microscope, just on the surface of these microbes, you see these small quantum dots. In order to understand mechanism, the cell with the microbe releases sulfur when they thread. So the moment you put this salt, they are going to become iron and is going to come touch the cell wall. The moment this iron comes on the cell wall, the cell or microbe, in order to save themselves, they release sulfur. Sulfur in a iron form. So what you have, cell is giving sulfur, you have moly ion, it becomes moly sulfide. Now this dynamics or kinetics of the reaction can be controlled depending on the growth of the cell. You can change the cell growth time, play around with it, you can control the dimension and so on. And this is a plot which you can see here. These are the different methods of or distribution of size by different methods, and this is where this naturally green material which is shown here, very narrow size distribution, very, the surface characteristics, most of them are constant. We utilize for biosensing, I'm not going to go detail, glucose, H2A2 sensing and so on can be done with this material. Also we can take this approach, make material which are not possible by normal conditions. For example, Nbium Carbide, if you want to make them, you have to really treat the material at 2000 degree or above. We put this Nbium fluoride, It forms niobium oxide with microbe, it can react and form niobium carbide of similar dimension with a defect which can be utilized for energy harvesting and so on. This opens the whole possibility if you can understand bio and try to utilize them for material synthesis, no energy, no environmental impact, green method of producing interesting material. Quickly, I'll not spend too much time here. The current generation of AI, machine learning, we want to see objects which are there in your computer, right? If I build something, I want to see them really in my hand, right? 3D printing allows us to do that. Any structure which is built in your computer, with 3D printing, we can print them with a certain limitation, resolution, we can make them in real objects, right? And that's another work which we started doing. We made tubulin structure. This is where Cristiano made the structures with an atomic scale. We may print them at macro scale. And printing this topologically complex structure, we can have impact resistance 3D printed structure as well. So plastic, when we talk about, we assume it's soft, weak. But if you engineer the topology, you can have porous structure with an impact resistance almost like metals. Apart from that, it has a lot of interesting aspect as well. If you have a metal object, when it bullet hits, what you see here is a deformation. Apart from that, you see the crack, what it means. In metal, during impact, you have a stress transfer. Whereas this porous structure of plastic, it doesn't just stop the bullet, you don't see any deformation at bottom there. It means it's going to protect the guy or human who is just below these objects, right? So there are a lot of other advantages we can add. We can print several of these geometries with high surface area, high porosity and good stiffness. We can print them. Now all these 3D printed objects with a high surface area can be utilized for any sorts of environmental treatment. For example, I take the object coat with zinc oxide, which can be utilized for cleaning water, right? Or we can put the other catalyst and put it in water or energy or environmental cleaning method, and they can absorb and clean the environment. We started looking at 3D printing of nanomaterial. We 3D print graphene, where we can have strength, we can tune ductility, we can have conducting 3D printed porous structure of graphene as well. We started looking at aligning the composite as well with 3D printing of direct ink. So what you do here is you take the matrix, put the graphite, make an ink out of it, and then print them. You can tune all sorts of processing condition, establish a relation between processing condition and their mechanical property, where you can introduce anisotropy in your composite. The last object is, okay, we can keep on printing this object, but can we really solve some interesting problem? After COVID or even today's generation, bone problem or orthopedic problem is a bigger challenge. What is really happened there is, suppose you have a bone replacement, right? The current bone material is made of hydroxyapatite, the ceramic. What is hydroxyapatite in brief? They take different elements, put them together, process them. Artificially, they make a material which is similar to bone. The problem in that material is it's not biocompatible. Second, the processing cost is huge, right? In order to make them, you have to really spend a lot of money. Now the question is, can we take something from nature and build some green material which can replace hydroxyapatite? So what we do, this is chicken curry, right? Out of chicken, you order them. If you take chicken, what you dump is this object. The bones, you throw them, right? Now what we do here is, you take this chicken bone and put them into certain simple chemical. For example, we put into H2O2 and then citric acid. Again, both of them you use in your household. Put them together here in a jar. If you dump it up, what you see after a certain time, depending on your concentration, you see a white powder collected. What are these white powder? The bone, chicken bone, is made of two different materials. One is organic, collagen, other is ceramic. Right? Now what the chemical treatment does, etch out the ceramic particle, right? So what you are doing is, you are creating a natural bone, or you are creating a bone from a natural bone material, right? And if you look at this powder, in ACM, they are small particles of 5 micron lateral dimension and 10 nanometer thickness, almost like 2D materials. Now what is the advantage if you have this kind of morphology? It's easy to make ink out of it because they can slide on top of each other. We take this material, put right rheology, and then you can print them. Because of this nature of or geometrical aspect, we can nicely align them. And if you do that, you can control its mechanical properties and you can print with a very high resolution. What you see here is the toe, the big finger, toe finger in your leg. Generally, if you hit somewhere, it's going to break. Now, the conventional joints like elbow, blah, 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 they're available quite frequently. But if you have a breakage like this, you don't have really commercially available solution. And if it's kids, it's even worse because you don't really get it in market. What you can do here is you take this scan, look at the broken piece, you can 3D print with a similar resolution. It has good strength, good ductility, all mechanical properties what you need they have. Apart from that, cell loves growing on top of it, right? So it's biocompatible, bio-friendly. We started working on this, printing several of them and try to look at its application. That's the direction where we are moving. We can utilize them for energy harvesting as well in generating voltage because of anisotropy. These are the different cover page which attracted attention of our work. As I summarized, these are the 4 different directions our group is working. I have not discussed the alloy development which is related to metals and alloys. This is the lab what we have, CVD lab. We have 3D printing lab, we have measurement lab here. We make large scale synthesis where we make them in 5 kilogram or 10 kilogram metal crystals. We can treat them, we can crush them in 2D form. This is my email ID. If you have question, you can see through them. These are the social media pages where you can get connected with that. Thank you.
Questions? I'll do the first one. Did the students eat the chicken?
So, this guy here, his name is Munojit. So he's the one who is doing this work. So he started working because his parents, he's his only son in the family. His father and mother both are surgeons. Okay, both of them are doctors, right? They do operation and so on. So he got excited about the project and he started working on. But he was making, how much chicken he will eat, right? So it's not just he alone. He started buying chicken and started giving to others. Say that, what you are eating today? Why you are vegetarian? Eat some meat, And he started buying chicken and give it to them. And as exchange of that, he was getting bones. So there was a time when he's making them. People are really happy because they are going to get chicken for free, right? So yes, they were really eating the chicken and getting the bone out of it. Also, he did another trick. So he talked to caterer, the guy who gives food in the marriage or function, and he started collecting the waste from there as well.
So what's easier?
Yeah, he just made this, and then he can, because we are talking about large quantity, right? If you want to print this object, we need not milligram, you need kilogram of it. So you need to have a lot of this. But now he has opened up a company now where he's talking to the boneless meat company where they sell meat without bone. It's very common now. What did this company, after cutting them, they take out the bone. He's buying from them also. And then that's what the company is resourcing the bone from.
Okay, and how about the 2 small?
Oh yeah, yeah, they are the one who are leading the group.
Years now, and we see quite commonly the graphene is amazing and it's great. It's the next step. What is currently like stopping it from being massively available just about everything? We do see some application of it, but why don't we yet see it in our science?
Okay, see, I cannot tell the physics aspect of it, right? As a material scientist, I can answer the material, right? Now, it's not that if you look at the human history, right? Let's go back initial age, Iron Age, Bronze, Brass Age, right? Look at the civilization. The name of civilization is given based on the materials, right? Now, if you look at all the material which is there in our society, what are the things common there? First, availability. Iron Age came because there are plenty of iron, right? Brass Age came because we have plenty of copper, right? So graphite is a good candidate. That is why graphene become hot. It's not that graphene was the first 2D materials. Physicists were working on 2D material for quite some time. They were making all sorts of deposited layers and so on. But graphene become very popular because you find plenty of graphite, right? But the second problem comes is ability to engineer them, to modify them, to process them, right? Till today, the graphene cost is fairly high. For device, if you want to get a wafer, they call it cheap, but still it's $200 A4 size. So some of the company, they make single layer graphene of this size, $300, right? Now think of your phone cost is, people are trying to buy as cheap as possible, $200, right? With everything. Now if the base material is so expensive, or can you do that? Answer is no, right? So that's the second thing which is limiting it. The third problem is stability. Silicon for electronics industry as a material is popular not because it's cheap or available, it's stable, right? Your phone, you keep it in sun, keep it in humid environment, it's stable. All these material like graphene, it's still a problem. You make a device out of it, controlling defect, controlling its real properties are difficult. They're not stable, right? So these are the three major problems, but yes, there are n number of these problems, we can discuss it. But any material you develop, you have to have these three things in mind. Is it available? Can we tune it? Can we engineer them? And is it stable? Otherwise, no one is going to use them, right? Some material will come, we'll publish several papers, get citation, get some, visibility, hype, but at the end of the day, we can't use them, or we will not use them in long term as well. But again, it doesn't stop us, but because what scientists are doing, they create a problem, then solve it, right? That's how life is, right? So this problem is lot of opportunity, but as an outsider, if you are not a scientist and you are looking at material, this is what you should see first, and that's what the company guys, they do. When we interact with them, they say, oh, it's exciting material, but can you give us 100 kilo, right? They say, how big you make? You say, oh, we made in a small vial. They say, what we'll do with it, right? For example, the coating industry. The requirement of the coating industry, the Berger, what we talked about, their requirement is per day 200 kilogram for the paint. Can you produce them in a cost which is feasible? Difficult. And that's what we solved. So we can tell about one example. In device, it's much more complicated, and there are several aspects they need to look at.
Well, I do have a question. Maybe it's a very elementary or naive one. I was trying to think of the process by which nature creates a material, so to speak, to the material, for instance. So what is the rationality? Is it about minimizing energy, or are there any other principles involved, like, for instance, I don't know, symmetry, entropy, or something like this?
Right.
Does it make sense? I don't know.
Yeah. What you said is right? As a material scientist, right, when we look at things in nature, things looks very complicated, like our human, right? There is nothing flat in our body, right? Everything is complex, right? Now if you look at material wise, there are few driving force which is universal, right? For example, the way your skin is going to grow, and the way your bone is going to grow, the way your teeth is going to grow, the way your hair is going to grow is completely different. Now think about in the same human body, you have so many variables, right? Now in nature, the variables are n, right? But when you try to look at growth, try to look at development, there is term called driving force, right? Yes, the driving force, that is something which is universal or can be made into universal, right? First is energy, right? Energy, whenever nature drives it, it tends to make minimum energy. First. Second is kinetics is governed by surrounding, right? Stuff which grows in open air, stuff which is going to grow under the sea is going to have environmental impact, right? So to conclude that what it depends on n number of factors. But if you try to bring all of them and see the center of it, I think entropy, it can be because of chemistry, chemical based, environment based. Entropy is one of the driving force, and second is energy. These two are driving. Now you say chemical based approach, at the end of the day you will see chemistry finally ends up minimum energy configuration, right? Chemical reactivity is going to have minimum entropy effect. So these are the two major driving force as a material scientist we look at. But when you talk about biologists, they will come up with a number of things. They'll say, oh, it doesn't really correlate with these two terms. But universally, you can't break these two. So you can come back and ask the question, the green 2D material I talked about. You say, oh, you are breaking, you are making material without energy, right? We can say that. But ideally, no. Someone is working for you, right? The cells are doing job for you. So you may not be building this, but microbes are putting energy there. So we can't break energy and entropy rules. It's going to be there. So if not you, someone else do job for you. Right? We thought of giving a title to the paper saying that slavery at nanoscale, but we realized that editors are not going to like it, right? But this is what we did, right? You take the microbe and ask them to do your job, right? And if you remember your kid, right? You can't do your homework, what you do? You ask your parents to do, or grandparents or friend, right? So the ideally in world or anywhere in universe, energy is the universal. It has to be minimum and someone has to do the job. That's it.
One last question. If not, let's thank Chandra again.
Thank you all.